are only basic things which we covered in the previous subjects also. So I hope everyone is comfortable with CO1 and CO2. Now we will start with CO3. Totally we are having 5 designing techniques in the entire syllabus after completion of the basics. Those are divide and conquer, greedy method, dynamic programming, backtracking, and branch and bound. Out of these 5 designing techniques in algorithms, 3 techniques are already completed in CO1 and CO2, that is divide and conquer, greedy method, and dynamic program, and a huge number of problems also you practiced for those 3 techniques. So after completion of those 3, we will continue with 2 more techniques in CO3 and CO4. Okay, so that is backtracking and branch and bound. So now we will start with backtracking concept. From today onwards, 2 weeks we will continue with backtracking and branch and bound, followed by remaining concepts is there in CO4, that is advanced concepts, NP hard, NP complete, PRAM, and some algorithms are there. Okay, we will discuss in CO4 after completion of these 2 techniques. Okay, so we will start backtracking concept now. So before going to the backtracking, some basic terminology is required to implement the backtracking concept. This basic terminology is graph traversal algorithms. Okay, everyone knows what is the meaning of graph traversal techniques, Bfs and DFS. These 2 techniques are graph traversal techniques for to search an element in the graph is there or not. So Bfs and DFS. So how to implement breadth first search and depth first search with BFT and DFT also, breadth first traverser and depth first traverser, BFS and DFS and BFT and DFT. How we will implement these things before going to this part? Okay. First, we want to learn what is the meaning of searching algorithm, or what is the difference between the previous searching algorithms and BFS and DFS. Previous searching algorithms are linear search, and binary search. After that, we will continue with BFS and DFS. After that, we will expand with BFT and DFT. What is meant by linear search? Where we will use that linear search for implementation. Where we use the linear search and binary search. These 2 concepts you have completed in DS na data structures. After that, these are also searching algorithms BFS and DFS. Linear search and binary search we will use for the set of elements which are there in the array or linked list. Okay, the sequence of elements. The elements are like, I will give one example for this. The elements are like 5, 2, 1, 6, 10, 9, 7, like this. These are the set of elements are given. I want to search 6 is available or 6 is there in the given list or not. For this type of technique, what type of method we have to use? That is called linear search. Because the given set of elements are not in sorted order, then we have to search the key element in the list in the sequential manner. That is called linear search. So set of elements are given in the form of array or something, that way of representation. You want to search an element in the given list, then you have to use linear search. Okay, suppose that set of elements are given. Okay, those elements are in sorted order. Those elements are in sorted order. I want to search the element is 6 is there in the given list or not. Is also searching technique, but the input is in the sorting order. Then you have to apply binary search. Okay, by dividing the given list by identify the middle element. If the middle element is less than or equal to the given element, okay, if it is less than, then you have to go for the first half. If it is greater than, you have to go for the second half. Okay, with less time, it can be searched based on the binary search. So these 2 techniques are searching techniques on the given set of elements in the form of array. So once we are comfortable with these 2 techniques, okay, the basic elements of array representation or something, then you will go for what is the meaning of binary search. It is also searching technique. how we have to differentiate with previous two searching techniques. So binary search is available, okay, on graphs. The input is a graph. Input is a graph. So everyone knows what is the meaning of graph, how it can be defined. Graph is a set of vertices and those vertices are connected each other. A set of vertices and set of edges, okay, is nothing but graph representation. So this is the given graph G, okay, with set of vertices and set of edges are defined. In this graph, I want to search an element 3 is available or not. I want to search an element 3 is available or not. How to search? What is the method you can use for searching an element in the given graph? Then you have to go for graph search techniques, that is called graph traversal techniques. These two techniques are the best methods to identify the element is belongs to given graph or not. So for that purpose, instead of this linear search and binary search, we will use BFS and DFS. Okay, there is a limitations for BFS and DFS. Those limitations we have to cover in BFT and DFT. Okay, there is a advanced techniques for BFS and DFS. So the main intention for the going with BFS and DFS is if any element you want to search in a given graph, then you have to use any one of the techniques of graph traversal, that is called breadth first search and depth first search. And these techniques are also well known to you in the previous concepts. Again, as per our subject, we will continue from basics onwards. We never script the basic concepts because those concepts are very, very important for all of you to implement the original techniques in algorithms. So first you have to go for BFS, breadth first search techniques. We'll go with best first search. Okay, how to implement best first search? So in a given graph, if any vertex you have to start with searching, that vertex first you have to visit. From that is called visit vertex. From that we have to continue with all the remaining adjacent vertices to the starting vertex. Once we are visiting all the remaining vertices, I will explain here. Suppose the given graph is 1, 2, 3, 4. This is the given graph, a set of vertices and set of edges. Suppose you are starting with one wedge. I want to search 3. I want to search 3, one element in the given graph. Okay, so I want to start with one element. This is the starting value. That's I want to assume as B. So that is a starting of searching, that is visited first. After that, how we have to expand the searching? That gives the method. Okay, that is called BFS is follow one logic and DFS will follow another logic. So what is the logic for BFS is, first you have to start the searching by using the starting element. So in this graph I want to start with 1. So I want to initialize with V value visited and it is expanded. So what is the next one is, we have to identify what is the neighbor nodes. For 1, what is the neighbor nodes? 2 and 3. First we have to visit those neighbor nodes. Okay, there is a vertex V is said to be explored. Algorithm, when algorithm is vertex, all vertices adjacent to it. First we have to visit all the adjacents to first vertex 1, that is 2 and 3. So all unvisited vertices adjacent to V visited next. Then new unexplored vertices means 2 and 3 are generated. What is the next step? Next you have to take one value in sequence 2, and what is the adjacent to 2? That is 4. Like this, we have to expand one by one with the new vertices. We will see one example, but this theory part, what is the technique we have to follow is, first you have to start with the starting vertex. Next, what is the next vertices we have to visit is, what are the all the adjacent vertices for the first vertex. First we have to visit all the vertices. After completion of that, next, what is the first vertex we are visited? From that, what is the remaining nodes are there, adjacent vertices, those adjacent vertices we have to visit. After that, what is the next sequence value? What is the adjacent vertices are there? We have to visit that. This is a level based search technique that is called BFS. Okay. What is the method? It is a simple method for the implementation process. That method is for any graph we want to search an element by using BFS. The given graph starts with one vertex by first calling the initial vertex of the searching. Based on the searching, we have to expand all the unvisited vertices. After that, what is the sequence of vertices we have to visit? The same way we have to expand remaining levels also. That is called BFS. In this process, we are using Q. What is the Q? What is the property of Q? Q is first in, first out. Before first in, first out. There is a property we have to justify with Q. So what is the sequence of vertices? Suppose from 1 I am visited 2 and 3. Okay, as per the BFS. What is the next expansion out of 2 and 3? Because those two are unexplored nodes, are live nodes. So which one I have to prefer? Which one is generated first? That can be expanded next. That is called first in, first out. After expanding 2, what is the next first element? That we have to expand next. Next 4 new nodes are generated. Which one we have to give the preference for expansion? What is the first node? That we have to expand. Like this we have to implement based on the Q. That is called before, first in, first out. So any graph we have to traversal by using vector first search BFS. So starts with one node and expand all the adjacent nodes, and based on the expansion, okay, if all adjacent nodes are completed, next you have to take what is the next first visit node or expanded node that can be considered. For that purpose we are using Q implementation. Okay, that is a basic thing we are using in BFS. Next one, we will solve by using one example by expansion of algorithm. So please see this algorithm before implementation of some example. What is the logic behind this BFS? There's the previous one is the theory part. They are explaining with words, but they are specifying it is our algorithm subject. They are mentioned with the same meaning with a sequence of instructions. So what are the instructions here? Any algorithm we want to implement, first you have to define that algorithm with arguments. So here the initial algorithm BFS of V. So what is the V is where you have to start the searching in the given graph. Suppose we are starting with 1, so BFS of 1 means 1 is the starting element. First you have to call this algorithm with initialized value out of the given graph where you have to start the searching initialization. That can be done by using this one. So that is BFS of V. So now V is equal to 1. So vertex V is equal to 1. We are calling that. In the BFS tree, we are using some array that is visited. So to know the status of each vertex, so what is the out of 7 vertices or 8 vertices, how many are there in the given graph? For each vertex, we are maintaining the status. This vertex is already visited or not. So there is a status initialization with 0. So the vertex is not visited up to now in the searching. So once we are visiting, suppose 2 is visited, then we have to update with 1. That is the meaning of these comments of the algorithm. So how you are maintaining the visited, okay, array? Visited array is nothing but in the given graph out of the set of vertices. So in the given graph it contains 6 vertices as per the example is concerned, as per the instance. All the 6 we have to maintain the array status. That is called this vertex is visited as the current execution or not. If it is not visited, that's why globally it can be declared and initialized with 0. Means initially all are zeros. Means we are not started working with BFS or any searching algorithm. So initialized with 0. When you are putting with 1, that is once it is visited, we have to put 1. Means vertex 2 is visited. After visiting 4, vertex 4 is visited. After visiting 5, vertex 5 is visited. Okay, like that we have to update the array that is called visited array. It gives the meaning of a particular vertex is visited as per the current calculation. That is called visited of 0 or 1. Next one, there is the logic starts here. First you have to take the internal variable u for cross checking or execution for expansion of the given node. Suppose we are calling BFS of 1. First we have to start the process with 1. That 1 we have to take with internal variable u. So u is the internal variable we are using for to process that vertex. What is the next step to expand the node? So u is equal to 1. Next one, what is the vertex you are calling? Means you are visited. That vertex you have to update the array with 1. Means visited of 1 is 1. Instead of 0, we are putting 1. Means that vertex is visited. All of you please observe, in this logic they are using repeat until concept. So there is a difference between while do and repeat until. What is the difference between while do and repeat until? While there is a condition, until we have to execute. What is the meaning of while do and repeat until? If the condition is true in a while, the condition is true, all these block of statements will be executed. The condition is true, then only this block of statements are executed. But what is the repeat until? Repeat until is also same control statement, na? So what is the repeat until? Repeat, a set of statements are there, and until there is a condition is there. What is the meaning of that? If the condition is true, then automatically it will be exit. If the condition is false, then automatically it repeats the loop. There is a logic behind the while and repeat until. What is the logic? If the condition in the repeat until, if the condition is false, then it repeats the loop. It goes to starting. When the condition is true, then it exits the loop. Okay, there is a basic terminology we are using, or in this algorithm, okay, they are using repeat until. That's why I want to give the meaning of repeat until compared to the while do operations. So what is the repeat until process? What is the logic behind this repeat until? As per BFS is concerned, for a given graph, once we are starting with one vertex, okay, how we have to expand the logic, or how we have to visit the nodes in the given graph. So repeat for all vertices W adjacent to U. So this is a U na. First we are starting with V is equal to 1, that is BFS of 1. We are calling BFS of 1. That's we are initializing with U. U is equal to 1. So what is the adjacent of U? So there is a number of nodes adjacent to, okay, U in the given graph. This is based on the graph only. We will explain with some example also. So all these vertices W which is adjacent means these values are W values. W is equal to 2 and W is equal to 3. Okay, for each and every adjacent of U we have to process. What is the process? If the visit of W, the status of visit of W, as per previous discussion, visit is a array na? Visited is an array. If the array, it gives the status of each and vertex. So as per current status of visited of 2 is 0, then we have to execute these two statements. Okay, add W to Q, or visited of W is equal to 1. Wait 1 minute. So if all visited of 0, we have to do this process. If visited of W is 1, okay, we will skip, means the condition is false. We have to execute these two. We have to execute these two statements. So is it clear now? This is a basic functionality. After completion of that, again we have to go with the false. Otherwise, we have to come to print. So this is a basic explanation for what is the meaning of each and every statement in BFS algorithm. After that, we will solve with some examples. Okay, we will implement the same BFS algorithm. So I would like to take one example in BFS for the implementation of same algorithm. Okay, with some values BFS. Okay, example. So all of you please note down this example when you are running nodes. Okay, I will take one graph, given graph G with 8 vertices, 1, 2, 3, 4, 5, 6, 7, 8. It is connected with all these 4 vertices, 4, 5, 6, 7. So some graph is available with us. We want to implement a BFS algorithm, how it can be executed to visit all the vertices. But the sequence of searching also is very, very important here. So before going to the execution, we know the procedure as per our previous discussion. First we have to take visit array visited of for all the vertices. We have to initialize it with 0. So 1, 2, 3, 4, 5. Totally how many vertices are there? 8. 6, 7, 8. So all these vertices as per the array representation, okay, all these vertices visited of this array must be 0. That's why before starting the process, I would like to take the array value that is 0, 0, 0, 0. For all these 8 values, initially visit value is zeros. Next, what you have to do once the initialization is over? First, you have to take the value of u. So, what is the first call? That is very important. Where you have to start the execution process. So, the first call of BFS, okay, that's we are starting with BFS of 1. In the total graph, where you have to start the searching the initialized value. That's why I want to use the first call of the BFS algorithm is BFS of 1. Means I want to start. So u value is b, BFS of b, u value is 1. So it is a u value is 1. Then we have to execute. You know the u value, if it is a 1, then automatically visited of v is 1. So what is the visited of v? So what is the visited of v? V is nothing but 1 now. So we have to put v is 1. So what is the result of execution of BFS? First we are visiting 1. This is the given graph. The result of execution step by step for BFS algorithm is first we are visiting 1. Okay, first we are visiting the result with 1. Next, what is the next step? As per the algorithm is concerned, first we are visiting 1 up to this execution is over. Okay, then we have to use repeat until concept. What is the repeat until? First, without any cross checking, this loop will be entered for all vertices w adjacent to u. So what is the u value? Current u value. What is the current u value? Current u value as per our calculation is, that is 1. So what is adjacent to 1 in the given graph? 1 is here. What is adjacent to 1? 2 and 3. Those values we are calling as per algorithm, that is w. What is w? All vertices of w adjacent to u. So how we have to call is, in the first calculation we are starting with u is equal to 1 and w is equal to 2, 3. So that is adjacent. In the first calculation of the algorithm, u is equal to 1 and w is equal to 2, 3. So if w is equal to 2, 3, we know w is equal to 2, 3. So what you have to do for all vertices of w means each and every vertex you have to process. For all vertices of 2, what you will do? You have to cross check for each w. Visitor of w is 0 or not. As per our current status, what is each w? First you have to take 2. What is the status of 2? The status of 2 is 0. Visitor of w is 0. Then please go to the algorithm. Visitor of w is equal to 0. These 2 steps you have to execute. What are the 2 steps? Please remind these 2 steps every time moving from previous slide to this slide is not required. What are the 2 steps? If the visitor of w is equal to 0, add the current node to q and visitor of the current node is make it as a 1. So next you have to maintain some q. As per BFS is concerned, q is nothing but everyone knows it is a FIFO, first in first out. First you have to make this w. What is the w status here? W currently it is 0. Then you have to execute 2 statements. What are the 2 statements? First, add w to q, means this q we have to add it to q. It is a q. Next we have to make visitor of 2 is 1. There are 2 steps as per algorithm every time. These are the 2 steps we have to do every time. If the visitor of w is 0, so next step. So w2 is over. Next, w is equal to 3. For every vertex you have to cross check the same condition. What is the w of 3? If the current status is 0. If the current status is 0, then what you will do? Again these 2 steps you have to execute. What are the 2 steps? That is visitor of w is 1 and add it to q. Visitor of w is 1 and add it to q. once your visited of W is 1, then automatically this 2 and 3 are visited. First we are visiting 2 and add it to Q, and we are visiting 3 adding key. So the result is the sequence is out of the given graph, out of 8 elements, first we are visited 1 in the sequence, next we are visited 2, next we are visited 3. This is the result sequence of elements in the step-by-step process. So up to 2, 3 is over. DFS of 1 evaluation is completed. If it is completed as per algorithm, for all these vertices, it is completed, then what we will do means up to this part is over. For all these vertices are W, so all are completed. 2, 3 we process it. What is the next step? Next, after completion of this for loop, we have to execute. What is the current status of Q? What is the current status of Q? As per previous calculation, 2 and 3 are there. So means it is non-empty. What is the condition is? Condition is always says Q is empty then return, means stop the process. So but Q is non-empty as per the current status. So this condition is not applicable. Next, what is the next step? Next step is delete U from Q. So what is the element we have to delete as per the process? Delete is always first in first out. Now what is the element we are moved? That element can be popped first. So now the element is removed from the queue. That element I want to assume as U as per the algorithm. So U is nothing but what is the element we are deleting? That element I want to assume as per the algorithm, that is U. So current value is U. After that the condition is false, is not true, then you have to go to the repeat. Means this algorithm will be continue until there is no element to process. That's the meaning of this. Okay, so it is false, then repeat. Repeat means same logic you have to repeat again. What is the same process? Again we have to identify all vertices W adjacent to U. What is the current value of U? U is equal to 2 na? So what is the adjacent vertices in the given graph? So 2 adjacents are W. So all the vertices adjacent to U we are named as W as per the algorithm. What is the W? 2 is adjacent to 1 and 2 is adjacent to 4 and 2 is adjacent to 5. Means 1, 4, 5 are adjacent values. If it is a 1, 4, 5 adjacent values, for all these adjacent values we have to do the process. What is the process we have to do? For all these adjacents of W, this condition we have to cross check. Please remember this condition we will execute for all the numbers in the general way. So each and every W is 0, then only we have to execute these two statements. So we want to cross check that. First one, visited of W, what is the current status? Visited of 1, is it 0? No, that's why we can't process anything. Because as per the condition, for only visited of W is 0, then only we have to execute these two statements. Otherwise we have to skip. Next one, visited of 4, what is the visited of 4? It is 0, yes. Then we have to execute those two statements, this statement and this statement. So we have to visit of 4 is 0, then what is the steps are? Visited of 4 is 1 and we can add it to Q. So means first we have to visit 4. As per the current status, we are visited 4 value in the sequence. So 4 process is over. 4 process is over. Next, what is the all vertices we have to cross check now? Until completion of that we have to continue the process. So W is 5. What is the current status of visited of W is? That is visited of 5. 5 is 1. Then we have to go for the execution as per the condition. These two steps you have to continue. These two steps you have to continue. That is add this 5 to Q and make this 5 as a 1. So 5 is visited now. In the sequence 5 is visited. So 5 process is also over. Once this W process is over, all the W's are completed, then for loop is completed. The remaining two steps are, what is the status of the queue? If the queue is empty, then you have to quit. If queue is non-empty, then you have to continue the next step as per the algorithm. What is the next step? Delete the current element or first element in the queue. That element we are making as a current element in the queue, that we have to make it as a U. So third step, U is equal to 3. Current element is 3. So we have to repeat the process. What is the process in the repetition? What is the next element in this process? u is equal to 3. What is the next step? If w, we have to identify what is adjacent to 3. 3 adjacents are 1, 6, 7. So what is the status of each and every one? We have to execute. We have to cross check. What is the 1 status? 1 is already 1, so we can't do anything. What is the status of 6? 6 is 0 as per the current status. Then 2 statements we have to execute. 6 we have to make it as a 1 and 6 we have to add to Q. Next 6 is visited. As per the current execution, make it as 1 is nothing but 6 are visited. Next one 7. What is the current status of 7? Is 0. If it is 0, make it as a 1 and add it to Q. And current node we are visited is 7. The sequence of visited nodes are next value is 7. So any other values are there in the W? No. Then we have to stop the process and exit the for loop. After that, what we will do? We have to cross check 2 conditions. What is the current status of Q? Current status is empty? No, because 4, 5, 6, 7 are available in Q. So we have to continue with delete the current element, means first element in the Q, that is 4, that is U. Next, what is the W? W is nothing but adjacent to U. So 4 adjacent is 2, 8. 4 adjacent values are in the given graph based on the example 2, 8. Those are the W values. So once you identify the adjacent values, each adjacent value you have to cross check the condition. What is the condition? First one by one. 2, is it 0? No. So there is no need to process anything. Next 8. What is the current status of 8? 0. Then we have to execute 2 statements based on the condition. Means we have to visit that vertex and we have to add it to the Q. So we have to visit vertex from 4 you are visited 8. That's why 4 to 8 I want to draw. So next vertex I am visited is 8. So that is the sequence. So 8 process is also over. So any other adjacent nodes are there to do the process as per the algorithm? No. Then we have to exit that for loop. We have to exit this for loop. Exit this for loop representation. Next, what is the next step? After executing, then we have to delete. Delete the current value from U. What is the delete value? 5. So next process is U is equal to 5. So what is the adjacent values for 5? Adjacent values is 2 and 8. So 2, 8 as per the given graph connections. So 2, 8. We have to process these 2, 8. What is the status of 2? 2 is 1. So we can't execute any other statements. Next 8. 8 is also 1. We can't do anything. So there is no expansion from 5 because all adjacent nodes are already visited. That's why there is no expansion. There is no new value. So once it's completed, then we have to exit the for loop. The statement is always Q is empty or not. Q is not empty because 6, 7, 8 is already there. Then we have to take 6. So U is equal to 6. So what is the W value as per the connections? W is adjacent to U, means 6 is the current value, adjacent is 3, 8. So 3, 8. Next we have to process all the adjacent value. What is the status of 3? 3 status is 1, so we can't do anything. What is the status of 8? 8 is already 1, we can't do anything. So there is no update based on U value. All adjacent vertices already visited based on BFS algorithm previously. That's why we can't update anything. Next one. After completion of the for loop, again we have to cross check Q is empty or not. If it is not empty, then take the value, that is U is equal to 7. So if U is equal to 7, what is the W values adjacent to U? So 7 adjacent is 3, 8. So how to process 3, 8? First cross check the 3. What is the status of 3? Is already 1. We can't do anything. What is the status of 8? Is already 1. We can't do anything. So there is no updation from U is equal to 7. So next one, cross check the Q. It is not empty and no node are added as per the previous calculation. So it is 8, U is equal to 8. How many adjacent nodes are there for V? For U, how many adjacent nodes are there? For representing W as per the given graph, 8 contains 4, 5, 6, 7. 4, 5, 6, 7. Based on the graph, 4 is adjacent, 4, 5, 6, 7. So what is the status of each and every node? The status of each and every node in the array visited 4 is 1, 5 is 1, and 6 is 1, and 7 is 1. So there is no updation. So after this for loop, again we have to cross check. Okay, based on this, queue is empty or not. As per the current status, after executing all the elements, queue is empty. If it is queue is empty, then what you have to do? Then you have to exit. If queue is empty, then return means you have to exit. Then you have to exit the repeat until and announce the result. What is the announcement of the result based on BFS? Not only this graph. This graph is for easy to understand visualization. We are using this sequence. But how we are executing the sequence is very important. That's why at the end of this calculation, we always mention what is the order of elements are visited based on this BFS algorithm. So for that purpose, we have to write the sequence every time in the execution process also for each and every calculation. What is the sequence of elements? Sequence of elements is visited based on BFS. What is the sequence? First we are visited 1, next we are visited 2, next we are visited 3, 4, 5, 6, 7, 8. As per this graph is concerned, this is the result. What is the sequence of elements you are visited based on BFS algorithm? Same graph we will use for DFS also. The order may be varies based on the logic. So this is very important for result explanation. But all of you please observe, if any graph we are taken, these algorithm based calculation implementation process for identifying how it can be executed. But the simple logic is, if any one vertex, suppose the given graph is this, given graph is this, is a simple graph, very easy to understand. Okay, how it can be executed in BFS or any graph. What is the simple logic is? First we have started with 1. Okay, that vertex is visited first. Next, what is the next step is, for the starting vertex, what is the adjacent vertices are there? Because all the vertices will be visited next. It is a step 1, level 1. Level 2, what is the next level is, all the adjacent nodes will be executed. So first we are visiting 1, next we are visiting 2, 3. Due to the reason of these are the adjacent to the previous visited vertex. Okay, that is a level 2. What is the next visited vertex means? As per the previous one, which one is visited first? That we have to expand all the adjacent nodes. Means 4, 5. Okay. Next, what is the next sequence? We are visited 3. So based on 3, what are the all the adjacent nodes? All adjacent nodes will be visited. Okay. So means for 2, 3, we are visiting 4, 5, 6, 7. Next level, all nodes we are visited in the Green graph. That is level 3. That is a level 3. Next, what is the next sequence? 4 is visited after 2, 3 as per the queue is concerned. What is the next level is there? Only 8. That is visited next. That is level 4. Nodes in the given graph. So it's a level based. Bet the first search. Bet means horizontal. So first we are visiting 1. Next, what are the all adjacent nodes? There is a level. Next level. Next, what are the adjacent nodes for the previous level? All nodes we are visiting. After that, we are visiting the next level. Once we are visited, there is node we are updating with 1. There is no need to visit again the sequence. Okay, that is called BFS algorithm based on queue implementation. Please remember it and don't confuse with BFS and DFS. Okay, for visiting nodes in sequence. I hope it's clear to all of you based on this calculation algorithm and this general explanation. If once you are confirmed that, then we'll go for next concept. Please type a message in chat box. If it is clear, then we'll continue with next. I hope it's clear to you as per your response. Then we'll go with the next concept. The next concept is, it is a continuation with BFS DFT, best first traversal technique. Okay, we'll go with algorithm or topic. After that, we will discuss with an example. It is very simple. If you know the BFS, BFT is nothing. By simply adding one logic for explaining this. BFT logic. What is mean by bet the first search? Bet the first technique. Sorry, bet the first traversal technique. What is the difference between BFS and BFT? Both are searching techniques, but based on the given input, we have to use either BFS or BFT. Where we will use BFS and where we will use BFT. Okay, both are graph traversal techniques. There is a condition here. If the given graph based on the given input, if the given graph is a connected graph, then we'll go over BFS. Okay, if the given graph is unconnected graph, then we'll go with BFT. Okay, BFT is not a new method. It is a method we will use recursively BFS algorithm. In BFT, internally we are using BFS more than one time. That is called a BFT. BFT is not a new technique. Here BFS is nothing but if any graph is given, previous example, with the first call only we are visiting all the vertices. BFS of 1. We never called BFS repeatedly in the previous example. What is the previous example? So some example we have taken now like this. In this example, some graph is given, then we are calling simply with one call BFS of 1 is the only call we are taken at the beginning of the calculation. So we are taking u is equal to 1 followed by all the remaining adjacent vertices. Finally, we are visited all the vertices 1, 2, 3, 4, 5, 6, 7, 8. All the vertices are visited with a single call due to the reason of the given graph is a connected graph. Given graph is a connected graph. Okay, connected and undirected graph. Then it is possible to visit all the vertices. Suppose some graphs are there. I will give one example for that. Some graphs are there. Those graphs are not connected. So what is the meaning of not connected? The graph representation. The graph is 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4 is connected and 5, 6, 7 is connected. This total graph is a single graph in this example. Okay, or some wise 8 is also there, that is also connected. This total value is a single graph, but in this total graph is not connected each other. So it is a one part. It is a one part, and this one is another part. Both are independent, but total value is a graph. Then how we are using searching some element 5. So first we have to call as per BFS algorithm BFS of 1. Then from 1, how many nodes we have to possible to visit based on the connections of 1. One adjacent is 2 and one adjacent is 3. First you have to visit. Next based on 2 you have to visit 4. So is it possible to visit 5? No, because 5 is not adjacent to any one of these 1, 2, 3, 4 nodes. So the searching is stopped here. Only possibility of this call 1, 2, 3, 4 only possible to visit. But how we have to search 5? The total graph is not visited now based on this example. That's why again you have to call BFS of 2. So 2 is already visited. That's why there is no result update. BFS of 3. There is no result because 3 is already visited and adjacent nodes also visited. BFS of 4. 4 is already visited and all the adjacent nodes are visited. Next you have to call sequentially BFS of 5. So BFT is nothing but it is not a new technique. the calling of BFS with all the vertices. So BFS of 5, once you are calling, then automatically the technique will start with 5. So the sequence is 5. Next, all the adjacent nodes we have to visit now. That is 6, 7 or 7, 6. Next, what is the next level? 8. So for the next call of BFS of 5, you are searching 5, 6, 7, 8 are visitor nodes. Next, you have to continue with BFS of 6. Next, you have to continue with BFS of 7. Next, you have to continue with BFS of 8. This type of execution we are calling as breadth first traversal technique. Okay, that is a basic method they are using for the repetition of n vertices. We are calling n number of times of BFS. For first call of BFS 1, these 4 nodes are possible to visit. Okay, next 2, 3, 4, there is no update because those all the adjacent nodes are already visited. There is no update. Next, for call 5, then you have to visit 6, 7, 8. Next call 5, 6, 7, 8 is nil report, means no updates because those all the adjacent nodes are already visited. This type of execution we are calling as, okay, that's the first traversal technique. Okay, at this moment, please cross check the result or the algorithm. Okay, what is BFS and what is BFT? Please see here. The same meaning is available in BFT algorithm or not? Please. Okay, please read sentence by sentence. What is the meaning of this? BFT is nothing but some graph is given and some graph is given with set of vertices. How many vertices are there in the given graph? So graph is given. Suppose 7 vertices are there or 8 vertices are there. Number of vertices in the given graph. Okay, that's the first traversal of the given graph. For I is equal to 1 to n, for all vertices 1, 2, 3, 4, 5, all are we are putting zeros because initialization we have done. Initially all vertices are unvisited vertices. Next, for I is equal to 1 to n2, what we will do is for each vertex which is not 0, okay, then we have to call BFS of I. Then you have to call BFS of I. Everyone is comfortable with how to call BFS of I. As per the previous calculation, BFS of I is nothing but BFS of 1. So after executing BFS of 1, as per this logic, what is the representation for that? You have to visit 1, 2, 3, 4. So 1 is 1, 2 is 1, 3 is 1, and 4 is 1. After that, again it can be go I is equal to 2, but 2 is already 1 because 2 is already visited. I is equal to 3, 3 is already 1 because you are already visited. 4, 4 is already 1. Then we never call BFS algorithm. Next, I is equal to 5. 5 is visited as per the previous? No. If it is no, then visited of 5 is 0 as per the current status as per 5. Then we have to call BFS of 5. Means same algorithm what we discussed previously, the same algorithm we are calling again. So 5 is nothing but as per previous one, 6, 7, 8. 6, 7, 8 are the, from 5 you have to visit 5, 6, 7, 8. So all we are putting as ones. So next, I is equal to 6, it is 1, I is equal to 7, it is 1, I is equal to 8, it is 1. So totally for this, as per this given graph, BFS called 2 times, one is for 1 and BFS another one is for 5. So 2 times it is called due to the reason of the given graph is not connected, unconnected graph. This BFT will work for only used for unconnected graphs only. If it is connected, then directly we have to use BFS algorithm. Okay, there is a difference and execution of BFS and BFT algorithm. So don't bother about BFT too much due to the reason of it is a repetition of BFS only for unconnected vertices. So I hope BFT is also clear. The same way we have to continue with DFS and DFT also. So at the beginning we discussed this concept, breadth first search and breadth first travel search, that is called BFS and DFT. These two are completed. Similar way, if you are comfortable with that, if you know that logic, then we will continue with DFS and DFT. Okay. Once you are say we'll go with DFS and DFT. Then I will continue with the logic and responsive. All of you please respond in the chat. So how do you know the graph is not connected or connected graph? Means please respond for this. There is a simple property of graph is connected or not. This graph is connected graph or not. Some graph is G is given. These are connected means all nodes are connected to each other from one node. Is it possible to reach all the nodes by using some path? If it say yes, then it is a connected graph. Connected means from any vertex, is it possible to visit all the remaining n minus 1 vertices? From any vertex, is it possible to visit all the remaining n minus 1 vertices? Therefore, it is a connected graph. Suppose I will draw one more example. 1, 2, 3, 4, 5, 6, 7, and 8. This is a graph 2. Is it connected graph? From 1, is it possible to reach 5? Or from 2, is it possible to reach 7? Or from 6, is it possible to reach 4? Because all nodes are related to graph 2 only. This total picture is a graph 2. So is it possible from one vertex of the graph to visit all the remaining n1 vertices? No. This is called unconnected graph. So for these graphs we have to use BFS. For these graphs we have to use BFT. There is a simple logic. If it is clear, then we'll go with the BFS. Say yes or no in the chat box. Very good. So we'll continue with DFS for the same example. Okay. Depth first search. So how to implement depth first search? Okay, it's very simple, like as a BFS, but it use stack representation, recursive call and stack representation. For BFS we are using queue representation, but here recursively we are calling as a stack representation. The execution is entirely different with BFS algorithm for a given graph. Okay, how it can be executed? Previously we are executing, suppose from one vertex, all the adjacent vertices we are visited first, all the adjacent vertices. Next from this we are visited all the adjacent vertices, like this. This process we are calling as a BFS. But in the DFS, it never visit all the adjacent vertices at a time. What is the logic is, suppose any vertex we are starting, what is the one neighbor vertex can be considered and visit first. After that, it can be take the current vertex is 2, and what is the adjacent vertices that can be visit first. Okay, from this, what is the adjacent vertices is there that can be visit first. Okay, like this it can be goes like as a depth, not breadth. Breadth is nothing but all the adjacent nodes you have to visit at a time. That is called breadth first search. Depth first search is from any vertex, it can be expanded based on one neighbor node can be selected which is not visited up to now. That node we have to continue. From that node again it can be identified what are the adjacent vertices. Only one vertex it can be selected and it can be continued. From that node it can be continued. From that node it can be continued for the next step. Like this it can be goes depth first. If it is no expansion, then only it can be comes to the previous step and next expansion. Okay, here any other expansion is there. Once we are closing all these adjacent nodes of depth nodes, then only it can we come back and expand the remaining nodes. This is called depth first search, the logic, and we will check how it can be implemented based on the same example which we discussed previously. Before going to that, first we have to visit the algorithm, okay, step by step, and the same example we have to continue with DFS also. What is the algorithm here? DFS algorithm. Okay, suppose the given graph is undirected graph with set of vertices and set of edges with n number of vertices are there. First the same logic of BFS, initially set to 0, visiting of all the nodes, and algorithm visits all the vertices reachable from V, and that is globally we have to maintain. So what is the first one? Visit of V is equal to 1, means we have to fix that vertex is already visited. Next one, for each vertex W, not for all vertices, please observe, each vertex is the keyword here. For BFS, all vertices W adjacent to U, but each vertex, one vertex only we have to calculate and start with calculation of DFS. If that vertex is 0, then we have to recursively call DFS algorithm. It is a recursive function. In BFS, we never use recursive function. It is a iterative function. So what is the logic behind this BFS and DFS is, once you are calling this recursive function, automatically all the current values we have to store in stack. All the current status of the execution we have to store in the stack. Once this recursive function calls is over, then we'll come back to the top of the stack and take the status of the execution and continue with remaining calculation. For that purpose, please observe they are not used any word here. It is a stack representation we are using for DFS, but in the previous BFS they are clearly mentioned, please add element to queue. Externally they are mentioned, please add an element to queue, but here they are not mentioned, add element to stack, due to the reason of internally can be mentioned it is a recursive function. All recursive functions, when you are calling a particular function calls itself, then automatically the current execution of the function can be stored in the top of the stack. That's why they are not explicitly mentioned that part. So the algorithm is very simple because it's a recursive algorithm. Number of steps are easy, but in the execution process we have to cross check it how it can be works for a given example for DFS. So because we are perfect in DFS, we'll go DFS in a simple manner. I will take the one example, the same example 1, 2, 3 to differentiate how it can be executed compare with BFS. So 6, 7, 8. Just don't listen like as a theory part. Please write yourself the same example and practice with the calculation. Then you never confuse at the entire your life. Okay, how BFS and DFS will work with logic. So this is a given graph. We want to cross check how the elements are traversal in a sequence way for this. So first initially we have to take visited array of each and every element 1, 2, 3, 4, 5, 6, 7, 8. Initially all values are zeros. All values are zeros initially. When you are visited, we are making as a 1. So once all values are 0, then what is the logic you are using is, first you have to call the algorithm DFS of 1. So that is V is equal to 1. So once V is equal to 1, initially all are 0, first visited of W is 1. So first we are identifying the result, that is you are visited in sequence first element. So the first calculation is V is equal to 1. We are starting with V is equal to 1. So what is the algorithm it mentioned? If V is equal to 1, we are putting visited of V is equal to 1. What is the algorithm for loop? For each vertex W adjacent to V, that's we need to identify. What is the adjacent to V? V is equal to 1 as per the given information. What is the adjacent values? 2 and 3. So W is equal to 2 and 3. So 2 and 3 we never process, okay, at a time. Then as per algorithm is concerned, each vertex W, that's what we have to take. Each vertex W adjacent to V. So what is the each vertex? Means first we have to take only one. 2 means only one vertex. Each vertex you have to process individually. First take 2. So after that, as per the condition, we have to cross check visited of W is 0. What is the W? 2. Visited of 2 is 0. Visited of 2 is 0. No. If it is no, then we have to call DFS of W. We have to call DFS of W, means DFS of 2. We have to call DFS of 2. So again we have to call the algorithm from the starting. We have to cross check the recursive way. So DFS of 2 we are calling means what is the DFS of 2? Like as the DFS of 1 we are executed na, same way DFS of 2 we have to take. Next, if DFS of 2 V value is 2. So DFS of V algorithm is there na, DFS of V. So DFS of V is nothing but, again we are calling, W is nothing but 2, automatically it can be goes to 2 here, V is nothing but 2. So if it is a 2, then visit of 2 is 1 as per algorithm. First value is visit of 2 is 1, this value. So once visited of 2 is 1, okay, then you have to visit 2 in the current state. So once it is visited 2, DFS works here from 2 only. So V is equal to 2. So again you have to process what is the W values here based on 2. What are the two adjacent values? 1, 4, 5. So what is the adjacent of 2? 2 is the current node. 1, 4, 5 are adjacent to 2. But at a time we can't take all. Okay, what is the logic in DFS? We have to take only one by one. So what is the one by one logic here? Is first visited of 1 is 0. No, visited of 1 is 1. So we can't call DFS. Visited of 4 is 0. Yes, visited of 4 is 0. Then you have to call DFS of 4. Okay, each vertex you have to cross check and call the recursive function based on the status of visited of the particular node. So visited of 4 is 0, then you have to call 4. Once DFS of call is 4, then automatically we have to say V is equal to 4. So previously 3 is not processed, currently 5 is not processed. You have to skip the current execution to DFS of 4, then you have to continue with the remaining calculation. So 4 is visited as per current status. Once it is visited, then you have to put 1. So visited of 1. Again you have to call DFS of 4 na. Okay, DFS of 4 is nothing but again you have to call DFS of 4 is 1 and visited 4 is 1. Then what is the adjacent vertices of 4? What is the adjacent vertices of 4? 2, 8. So what is the 2, 8? Again you have to cross check. What is the status of 2? 2 is already visited. So we can't call DFS algorithm. What is the status of 8? 8 is already 0. Then we have to call DFS of 8. So once DFS of 8 is called, then the next calculation will come to the picture. V is equal to 8. V is equal to 8. Once it is V is equal to 8, then go with what is the adjacent nodes of 8. So first you have to put 8 is 1. So 8 is visited. 8 is 1. 8 is visited. So what is the adjacent to 8? 4, 5, 6, 7. So based on the 4, 5, 6, 7, what they are specifying, each vertex you have to cross check the condition. Okay, each vertex means first we have to take 4. First you have to take 4. 4, what is the status? 1. Don't call DFS. Next take 5. 5 is 0. Then you have to take 5. Then call DFS of 5. Once DFS of 5 is updated with 1 and 5 is visited, and the next value of V as per DFS call, it is 5. So what is the status of 5? Next expansion. What is the adjacent nodes for 5? 5 is visited, that is called W. What is the adjacent to 5 as per the given graph? 2, 8. So what is the status of 2? It is 1. What is the status of 8? It is already 1. So don't call any DFS algorithm here due to the reason of each and every vertex is already visited. So there is no expansion from 5. So depth is closed here. When depth is closed, please identify this logic. When depth is closed, what you have to do? It is a recursive function. Once you are going from one function to another function, this calls another function, this calls another function. This execution is over, all the statements. Then what you have to do? You are calling from C now, you have to come back to C and all the remaining statements you have to execute. If the C function is also over, then you have to come to B and execute all the remaining statements. This is also over, then you have to come to A, execute all the remaining statements. This is the logic for recursive function. The same logic we will use here by using stack representation. Once the calculation of 5 is over with all the values, then we are not closing this entire function. We will come to the previous one. What is the previous one? Up to 5 only we are completed. 6 and 7 are pending. those expansion of 6 and 7, then you have to call DFS. Remaining vertices you have to execute DFS of 6. So remaining execution is starts with U value as a 6, V value as a 6. If it is a 6, then what is adjacent nodes? 3, 8, W value. So what is the status of 3? It is 0. So DFS of 3. DFS of 3 means from 6. DFS of 6 we are calling now. Then we have to make 6 as visited because 6 is updated with 1. Once 6 is updated with 1, then we have to continue this process. It is a DFS of 3. We have to call the 3. Then we have to update with 3 value is also 1 in the recursive function representation. Once it is updated, then we have to go with the calculation of DFS of 3. That is V is equal to 3. Once it is V is equal to 3, okay, what is the adjacent nodes are there? 1, 6, 7. W is equal to 1, 6, 7. So what is the status of 1? Is already visited. What is the status of 6? Is already visited. What is the status of 7? Is not completed. Then we have to call DFS of 7. So once it is called DFS of 7, 7 is updated with 1. Okay, and we have to call with V value is 7. So once V value is 7, what are the adjacent nodes are there? Those adjacent nodes are 3, 8. What is the 3 status? 1. What 8 status? 1. So all values are completed. Once the 7 calculation is over, then where you have to go with? Go with previous execution. What is the 7th? 7th is already completed. Go with next one. Up to 6 is over. What is the DFS of 7? There is no vertices. Again come back. 8th is not completed here. If 8th is not completed, then again you call DFS of 8 is already over. Next comes to previous step, that is 4 is available. DFS of 4 is only completed. 5 is pending. Again you have to call DFS of 5. So what is the 5 value? 2 and 8 are adjacent to 5. So 2 and 8 are already visited as per the calculation. That's why this calculation is also over. Then comes to previous. Up to 2 only completed in the previous. 3 is pending. Then we have to call DFS of 3. What is the 3 value? Adjacent nodes are 3 adjacent nodes are 3 adjacent 1, 6, 7. So 1 is already visited, 6 is already visited, 7 is already visited. There is no expansion. So any other further process is there? No. Then we have to stop. So this is the execution process of DFS algorithm. But please observe, this is very important. What is the sequence of elements you are visiting in this searching process? That is very important to conclude the result. What is the result here? Is not just this graph. Not only this graph representation. This graph represents the pictorial representation of what nodes are visited. But the sequence is: first we are visited 1, next we are visited 2, next we are visited 4, next we are visited 8, next we are visited 5, next we are visited 6, next we are visited 3, next we are visited 7. This sequence is important for DFS algorithm implementation. Starts with 1. So this is the result. So same graph we are using for BFS also in the previous example, and also we are started with 1, BFS of 1, but what are the nodes visiting sequence? 1, 2, 3, 4, 5, 6, 7, 8. But DFS, the story is different here, is the sequence. For BFS, this is the sequence. That's why the sequence of visiting nodes is very important instead of this graph representation. That varies how it can be executed. Okay, I hope it's clear. It's executing based on depth representation. If depth is closed, then you have to expand. The expansion is closed, then go to the previous step. Okay, this DFS is very important compared to this previous DFS, because in the backtracking we always use DFS only. Means how we are backtracking here. First we are starting here up to the depth. If any solution found, we have to give the result. Otherwise, you have to come to the previous step. Next expansion you have to make. If all the expansions are over, then you have to come to the next previous step. If any expansion is possible, we have to expand. If all the expansions are over, come to the previous step. If any expansions are is possible, then you have to expand. This type of process we are calling as a backtracking. Our next chapter is backtracking. We always use this type of calculation in the backtracking representation. I hope this concept is clear for DFS, how it works based on the algorithm. then we'll continue with BFT. Okay. Please type in the chat box.
Sir, sir, your voice is not audible, sir. Krishna Reddy, sir.
Hi, is it clear now? Is it clear now? Is it clear now?
Clear. Continue, sir.
Yes, sir. Now it is audible, sir.
Now it is clear, sir.
Okay, thank you. So, what is the difference between DFS and DFT? DFS is for any given graph is connected in a single call of the graph, we will search or we will traverse all the elements in that graph by using some sequence of logic. If the given graph is unconnected graph, like if all the elements are available but those are not connected to each other, like this is a single graph with 6 elements, then we have to use to search all the or visit all the vertices, you have to call DFT. DFT is nothing but it's the recursive call of DFS. First you have to call DFS of 1, then automatically you have to visit 1, 3, 2. Okay, after that there is no possibility to reach 4, 5, 6 because those are not adjacent to the previous 1, 2, 3. Again you have to call DFS of 4, then you have to visit 4, 5, 6 in sequence. Okay, based on the depth, first you have to start with 4, depth 5 is not possible to expand from 5 because 6 is not adjacent to 5. Again you have to come back and visit the next vertex 6, 4, 5, 6. In 2 calls with this example, we have to visit all the vertices. This number of calls of DFS is nothing but DFT. The same logic of BFS and DFS. So these are the 3 techniques we will use for graph traversal. And one more technique is there. It's also very simple. It's there in the previous next chapter. Again, we have to continue here because all similar concepts we will complete here. D-search. Any one of you know D-search? Any one of you please respond in the chat box. What is meant by D-search? Up to now we are completed BFS based on the queue representation, and DFS based on the recursive call is nothing but stack representation. Okay, those 2 are traversal techniques. Same way, if any graph we have to search an element by using D-search. Okay, then what is the logic for D-search? So queue is already used here and stack is already used in a sequence manner based on the adjacent vertices. What is meant by D-search? Any one of you? Any one of you know, please say yes. Don't write any logic in the chat box. If you know or not, that's more than enough. If you know, I will explain the logic. If you don't know, I will explain the logic in depth. That's the only difference. If no reply means you are not listening my words. Only one response is there is nothing but only one person is listening our words. The chat box indicates that how many people are listening the class in attentive manner. Only 2 persons. So all the remaining people are sleeping after logging. Hosts are please once unmute all. We will cross check what is the status of all the students. What is their backgrounds? They are listening music or playing with some other things, or they are in the outdoor. Sir, host sir, Suresh sir, please unmute all. Subbarao sir, please unmute all.
Okay, sir. Okay.
We will cross check the background voices. How many are active? How many are listening? And how many are doing other works by just logging? How many are there?
ఎంత చదివినా డాక్టర్ అంటే ఇంత కష్టం చెప్పాలి.
Hello, sir. సార్ వినిపిస్తుందా సార్ మీకు?
వినిపిస్తుంది సార్.
సార్ వాళ్ళని అన్మ్యూట్ చేయమంటారా సార్ స్టూడెంట్స్ని?
మ్యూట్ చేయండి.
అన్మ్యూట్ చేయమంటారా సార్?
మ్యూట్ చేయండి.
మ్యూట్ చేసేసింది సార్.
Okay, very good. So that gives the meaning of how many people are listening the class with attentive manner. So that gives only the feedback. Okay. Only 30 students they mentioned. We don't know what is the meaning of D set. Remaining all people they didn't bother about what is the current topic and what we are discussing. How much you know. Okay. There is a feedback based on the chat box. Only 30 out of more than 500. It's good. It indicates that okay, how you are listening the class. Thank you. So we'll go with D search compared to the BFS and DFS. D search is nothing but it is a simple search technique. Algorithm and everything is that much is not required. BFS plus stack representation is nothing but a D search. It's very simple. Okay, D search is nothing but the execution of as it is BFS, but instead of Q we are using stack. Instead of Q in the algorithm BFS we are saying every time adjacent vertex please add it to Q. Instead of that please use stack. So how it can be executed? We will cross check it. The same example because we will differentiate how it can be executed for the same example. We will get the clarity. Okay. So how it can be executed? D search of 1. First we will call with 1. D search of 1. So we will maintain stack. Stack is always last in first out concept. Previously we are using for BFS is a queue. Okay, first in first out. So D search we are calling D search the same as BFS algorithm. How it can be works? So first we are calling 1. So first visited of 1, 2, 3, 4, 5, 6 we have to maintain the array na. 1, 2, 3, 4, 5, 6, 7, 8 visited nodes. Initially all these nodes are zeros. All these nodes are zeros. So first we are calling D search of 1. If 1 you are calling D search of 1, then automatically visit of 1 is 1 and visit of vertex 1 is completed, and next one is for all the adjacent vertices. How many adjacent vertices are there for 1, 2 and 3? For all the adjacent nodes of 2, 3, if it is visited is 0 then make it as 1 and please add it to Q. So please add it to Q. Okay, either both concepts are acceptable. I will explain this. What is the meaning of that in the reverse order? Okay, how it can be executed. Initially it is zeros. First you have to visit 2, then you have to make 2, make it as a 1. Next you have to adjacent 3, then you have to make it as a 1, 3, because it is all zeros. 3, that is a stack. So what is the top element? Next, any adjacent nodes are there? No, you have to stop that. What is the status of the stack? Is it empty? No, it contains 2 elements. Then we have to go with what is the top of the stack. Remove that. That's we have to assume as V. Okay, so V is 3 is nothing but we have to expand 3. What is the adjacent nodes for 3 as per the list? 1, 6, 7. So who are contains 0, 6 and 7 are 0. First you have to visit 6 and 7. First you have to visit 6, make it as a 1 and add it to stack. Next you have to visit 7, you have to make it as 1 and add it to the stack. Okay, next after expansion of 3, what is the current nodes? Okay, which are unvisited. What is the top of the stack, or what is the status of the stack? Is it empty? No. Then what is the top of the stack? 7 means expand 7 next. What is the possibilities of expansion of 7? How many adjacent nodes are there for 7? 3 and 8. How many are status 0? 3 is already 1. Status of 8 is 0. That's why we have to visit 8 from 7. So we have to add to the top of the stack and update with 1. So what is the current status of the stack? Is it empty? No. Previously in the BFS, what is the status of Q? We are checking every time. Status of no. Then we have to start with 8. 8. What are the adjacents of 8? 4, 5, 6, 7. 4, 5, 6, 7. So what is the status? Is the BFS now? Any adjacent nodes of 8 that can be visited first. Okay. All adjacent 6 and 7 is already visited. Next 5, 4. All the adjacents are 5. Means first we are visited 4. Next we are visited 5. So 4, 5, 1, 1. Next we have to expand 5. Any adjacent nodes are unvisited now for 5. 5, 2 and 8. 2 and 8 is already visited. 2 is 1, 8 is 1. So next 4 we have to take. 4, 2 and 8 is already visited. There is no 0 concept here. Next 6 is pending. Any 6 value 3 and 8. 3 and 8 is already visited. There is no expansion. Okay. Then 2. What is the status of 2? 2 adjacent nodes are 1 and 4 and 5. 1, 4, 5. Status is 1, 4, 5 already visited. So there is no expansion. So what is the sequence here? First 1, 2, 3, 6, 7, 8, 5, 6. This is the sequence of D search. This is the sequence of D search. D search is very simple to know the logic. Is BFS algorithm as it is, please write. Please replace in the place of Q with stack. Remaining logic is 100% same. So the sequence is different. What is the sequence for DFS? We are visiting 1, 2, 3, 4, 5, 6, 7, 8 in sequence. It is called BFS algorithm. For the same example, the sequence of visiting vertices is 1 to 8 in order, and D sets for the same example 1, 2, 3, 6, 7, 8, 5, 6. Sorry, 6, 7, 8, 5, 4. Sorry, last element is 4 because we are visited. This element is last now. 5 followed by 4. 4 followed by 5. Whatever. Okay, that is called D sets. This algorithm is also very important. Okay, for the implementation process. Once you are confirming these 3 algorithms are comfortable to you for the implementation of backtracking, then we will go with what is the general logic for backtracking implementation. So traversal techniques are over. All these are over. I hope everyone is clear. D search tree is also available here. This is an example. One more example is a lengthy example. First they are starting with 1. Next they are expanding 2 and 3. In BFS they need to expand first 2, but here they are expanding 3. That is called 4, 5. That expansion is done from 3 instead of 2. In BFS we have to expand 2. What is the node first we are visited that can be expanded? It's children's. But here what is the last node visited? Based on the previous adjacent vertices that can be expanded. 4, 5. What is the last 2 node? 5. That's we have to expand first. 6, 7. Out of 6, 7, what is the last value? 7. That's we have to expand 8, 9. Once this depth is over, means all the adjacent over, then you have to come back. Then you have to come back. Next we have to expand 6. That is previously it is 9 is over, 10, 11. Any expansion is over. Come back. Is a stack now? Come to the top of the stack again. Again come back. After 3. Okay. Next you have to expand this. That is previously 11 is over, 12, 13. Next 13 is the latest, is the top of the stack. Next 14, 15. After that come back. Come back to the 4. Expansion, next expansion 12, 16 and 17. The nodes numbers are generated based on D search. Okay, means based on stack representation. What is the recent visited node that can be expanded first? Okay, what is the recent node that can be expanded first? If the recent expanded node there is no possibility to expand or to generate the next level, then go to the previous unvisited node. Okay, next you have to expand. You have to draw the graph based on this in the reverse way. But in the BFS, you have to use expansion in the horizontal manner. Suppose the same thing 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7, 8, 9, 10, 11, 8, 9, 10, 11, 12, 13, 14, 15. This is the way in BFS. But D search, this is the logic. We have to expand this. First we have to expand both. What is the recent one? That's we have to expand. What is the recent one? That's we have to expand. What is the recent one? That's we have to expand. Expansion is closed. Then come to previous one. What is the previous visited node? That's we have to expand. After this, again come back. Next, what is the recent one? That's we have to expand. What is the latest one? That's we have to expand. Like this is called D search with another example of how we have to generate this depth first search. Okay, clear? Then we'll go with next backtracking. Once you are perfect in the previous concepts, so this logic is very simple. Backtracking logic. If any problem is given, what is the meaning of backtracking methodology? If any problem is given in the backtracking, we have to simply use DFS logic. Okay. If any problem we want to solve by using this method, this is the fourth method, designing methods in algorithms. First we are completed divide and conquer and greedy method. Next dynamic programming. These three are completed. Next we are going with backtracking to solve a given problem. How to solve the given problem by using the backtracking? What is the terminology we are using, or what type of problems we can solve by using backtracking concept? If any problem is given, then it can be specified in terms of constraints. Those constraints are implicit constraints and explicit constraints. I will explain what is the meaning of implicit and explicit constraints also. That is there in the theory part. Okay. After that, based on these constraints, we have to produce the solution. Any problem we are given with set of rules. Okay, we need to follow for solving the problem. The set of rules also dividing into two categories. One is implicit constraint, another one is explicit constraints. Based on these set of rules, we have to give the solution. That solution in this backtracking is in the form of solution vector. Solution vector means any problem we can give the result is in the form of this solution vector. The general notation means if any solution, suppose 1, 2, 3, 4, 5, 6, like this type of elements are there. This is called first element I is equal to 1, I is equal to 2. That is called xi, x1, x1, x2, x3, xi, xn. Means any solution in this backtracking we are representing with solution vector. These solution vectors are how to get these 1, 2, 3, 4, 5, 6. This is from one set of possible values based on the given problem. From the set of given problem possible values, we will identify which values it gives the solution. Those values we are representing in the form of vector representation. So in this backtracking notation, any solution we are representing, okay, that solution is in the form of, please remember it, at the end of the each and every solution in the backtracking, we are always represents with a solution vector notation. Don't write just like as a graph and some tree or some graphical notation and say this is the solution for the given problem. Each and every solution in the backtracking must be given in the form of solution vector only. Okay, what is the meaning of the solution vector is that problem in the vector which gives for either maximize or minimize the given criterion function. Criterion function is nothing but is a condition. What is the set of rules are given that is either maximize or minimize the function, that is called a solution vector to find a vector for the solution. The major advantage of this method backtracking everyone knows. Okay, what is the major advantage? Like as a DFS, suppose we are starting the solution with one element. Suppose we are expanding based on DFS 2, based on next expansion 3. From 3 we have to expand 4. From 4 there is no possibility to expand to get the result. Then automatically there is no need to expand this. We have to use the backtrack and expand the remaining possibilities. Okay, here also there is no possibility to expand to get the solution. Again come back and move to the previous step and identify the solution by using another path. So backtracking possibilities, there is no need to expand the entire all possibilities of the given problem. If any such situation we identified there is no possibility to reach the solution based on this path, then you have to stop the path based on this criterion function or something. Then we have to go to the previous step and move to the expansion in the another path. If there is no possibility, again move one step to previous and identify the next path. So to save this calculation, okay, is the possibility or the best technique we are using backtracking concept. So there is a one advantage by using the backtracking. Backtracking is nothing but it is just implementation of DFS algorithm. Okay, so please listen some terminology before going to solving some example. 4 examples we are here. We want to solve based on the syllabus. Before going to that, we want to know what is the meaning of the terminology we are using in this backtracking. Okay, require the solution to answer the complex set of constraints. These set of constraints they are defined in terms of 2 parts. One is explicit constraints, another one is implicit constraints. Okay, there is a meaning of what is the meaning of explicit constraints is nothing but if every time we are specifying that for the given problem solution is representing in the form of solution vector, means some sequence of values. This vector, what type of values we need to consider? What is the constraint for selecting these values? That is nothing but explicit constraints. Explicit constraint is nothing but every time solution vector we are representing with x1 to xn, okay, with some values. Those values, what is the possibility to take these values we are representing in a explicit constraint? Suppose the values, what is your age? Okay, then what are the possibilities of the values? Those values are greater than or equal to 0. So any values you are right. Please select any 5 members and write their ages. Our best 5 members write their ages. So we have write the ages of 5 members. What are the possibilities of this set? The set it contains the general values 0, 1, 2 up to so on 100, 110, 150 or like this. These are the possible set. From this set you have to write any 5 values. That is called the possible set is representing what is the set of constraints to represent the solution vector. The possible values is nothing but. So some they are giving some possibilities. Some values are greater than or equal to 0 based on the problem. Sometimes it is a result is a boolean value. Suppose knapsack problem is there. What is the knapsack problem? 0 knapsack problem. Everyone is comfortable with that. 0 knapsack problem and normal knapsack problem. 0 knapsack is nothing but suppose 4 objects are there for the given problem. To identify the maximum profit, which objects we have to place in the knapsack. So it is 0 1 means only 2 possibilities. The object is selected or rejected. So second object is selected, third object is rejected, fourth object is selected. This is an example. So based on second object, fourth object selection, you will get the maximum profit value. So how to represent the solution? The solution is always contains 2 possibilities. There is either xi is equal to either 0 or 1. That is the meaning of solution vector. What is the possibilities of Si for the knapsack 0 1 is nothing but either true or false, means selected or not rejected. Okay, there is one type of examples they are using binary representation 0 or 1. Some type of examples they are using xi is nothing but greater than or equal to 0, all positive integers. Some type you have to specify the range also. Suppose normal knapsack problem, please consider how to represent the solution for normal knapsack problem. Normal knapsack is nothing but decimal part is also acceptable, na? Partial object is also acceptable. So the range is 0 to 1, means 0.3 portion of the object is possible, 0.5 portion is also acceptable, 0.7 is also acceptable, or full object is also acceptable, or rejected is also acceptable. So the range is 0 to 1. So xi value is in between 0 to 1. The range is also acceptable. This is called the possibilities of solution set is also acceptable. So range is acceptable, or some selected value is acceptable, or some this type of representation is also acceptable. So always implicit constraints. Please remember the next 4 examples we are solving in the backtracking. Explicit constraint is nothing but we are simply specify that for the result representation, what type of values we are selecting, those values set is nothing but is a explicit constraint. Next, implicit constraint. It is very simple. Implicit constraint is nothing but what type of conditions we are using to select a criterion function. Okay, what is the criterion function? What is the condition we are implementing to get the solution? That is called implicit constraints. Okay, these are the 2 constraints we are using, explicit and implicit. Explicit is nothing but what are the possibilities we are using for representing the solution. Implicit is nothing but to get the solution for a set of solution vector representation. What is the criterion function? We have to satisfy that given representation. Okay, there is a representation for implicit and explicit constraint. All of you please observe here. This is called backtracking general method. Backtracking general method. For any problem, this common condition we need to apply. Okay, instead of the basic problem constraint, this is a common procedure for backtracking. What is the common procedure here? It's very simple. If you know DFS, it's very easy to identify the meaning here. If any solution is given with n input values, okay, finally we have to generate some solution vector, means some representation, that is x1, x2, x3 up to so on xn. Some solution vector we are representing. First you have to start with k is equal to 1, means you have to initialize with k is equal to 1. When k not equal to 0, then all the remaining untried values, okay, that x of k is equal 1 to k minus 1. Suppose it is a k value. Suppose I want to execute some extend 3. I want to assume it is a k. Now that is k is equal to 3. I want to process for easy to understand. What I want to cross check is this x of k is belongs to all the previous values. It satisfies all the previous conditions, and this boundary condition is true. Means for each and every problem they are specifying some constraints, that is called implicit constraints is represented as a what is the condition. This k is satisfy the implicit constraint boundary function, then only we have to go with next step. What is the next step is, if this boundary condition is satisfied, if it produce all the answers, then it is a answer node, produce the result, or otherwise please expand the next node, means k plus 1. Okay, every node we have to cross check in the DFS. Okay, up to previous n minus 1 k minus 1 nodes are available in the tree, and the current node is satisfying the boundary condition. Both conditions are true. Then we have to cross check, is it produce the solution, means answer or not. If it is answer, then it displays the answer. Otherwise we have to expand that node to the next expansion. Okay, for 4 also, suppose it is a k. Please identify all these k minus 1 are expanded and boundary condition is satisfied. If it is an answer node, then display the answer. Otherwise we have to expand to the next node. Okay, up to this consideration we have to continue, and one more step is also there, else part. Suppose there is no expansion from 5, what we have to do? We have to do with k minus 1, means we have to move one step to previous. The same technique we are using in DFS also. Okay, we have to expand in the backtracking in depth first manner. If any situation there is no expansion, there is no next step, then we have to block it and we have to make k minus 1 to the previous step. Again you have to continue with the next step. Okay, if it satisfies all the criterion function, okay, all the k minus 1 is also available in the tree, then we have to make the answer node. Otherwise we have to expand k plus 1. If it is not possible, then you have to move to the k-1. Like this, you have to implement step-by-step process. These all the concepts we will implement with the given examples by generating the values with a general method. Please remember this method is same as DFS logic only. Okay. Thank you. In the next class, means afternoon 1:10, we will continue with the basic terminology of state space tree. These all the techniques, and we will continue with two more examples. One is graph coloring problem, another one is 8 puzzle problem. Thank you very much for listening. 100 minutes time. Okay. Today afternoon again we will continue with remaining techniques of backtracking. There is graph coloring problem as well as n queens problem. Thank you. Thank you, Sir Subbarosa.
Sir. Thank you, sir. Thank you. Can I end the session, sir?
Yeah, please.
Okay. Yeah.